Alright, so in this video we're going to talk about some examples of the integral test, and what the integral test is, of course, and also some ideas about estimation of series. So here we go. Up to this point, we have only had direct calculation of the nth partial sum to either decide convergence or divergence of the series. We had the geometric series result, right? What else have we had up to this point? Nth term test. Right? What else is in our arsenal? That's pretty much it. These are the tools we have to bring to bear to decide the convergence or divergence of a given series. So now we will add a few new tools to decide the convergence or divergence of a series. In particular, we're going to learn the integral test and the p-series test, or result as I sometimes call it. And we'll also study the associated estimation result, which tells us how close the nth partial sum is to the total series, right? In fact, these pictures tell you why the integral test is going to work. Let's look at it. So this is a picture here. So if we have the integral from 1 to infinity of f of x dx would be the area under the curve, right? And I've drawn boxes to illustrate the area that corresponds to the term in the series a1 plus a2 plus a3 plus a4 plus a5, . So if you look at this integral, this improper integral from 1 to infinity, it should be larger than or equal to the sum of a2 plus a3 plus ... right? So if we wanted the whole series, it would be, certainly it should be smaller than a1 plus this thing, which is smaller than the sum of the second term out to infinity, like that, right? And so that would be some logic if we had a continuous function, positive terms, right, and they were decreasing. That would give us a way to compare the value of the series to the value of the corresponding improper integral. And that is the, in fact, the integral test, as I'll state more carefully here in a bit. On the other hand, right, if in the other direction, if we picture the boxes corresponding to the series a1, a2, a3, right? That's at 1, this is 2, this is 3, this is 4, and so forth. Well, then you can see that the area under the improper integral should be less than or equal to the sum of the whole series, because, you know, it's a little bit bigger, a little bit bigger, a little bit bigger, right? So we get this estimate. We have the integral from 1 to infinity of the function f of x dx. And by the way, this function we're comparing, it's the function which, I think I should have said this already. It was in the screen, I hope, but we're assuming that the function matches the sequence at the, at integer values, 1, 2, 3, 4, 5, and so forth. And then f is a continuous extension off those values. All right. So for these pictures to make sense, f must be positive, continuous, decreasing, matching the sequence at integer values. And in summary, from inequalities 1 and 2, put them together, we have that the series is pinched between this improper integral and in itself plus a1. So this gives us a bound. It says that the series, if it converges, it has to converge between that and that. That's it's pretty neat. And so that in fact is the integral test. So here it is. I'll just state it careful as I know how. Suppose f is a continuous, positive, and decreasing function on 1 to infinity, and let the sequence a sub n be equal to f of n for n in the natural numbers. Then the series is convergent if and only if the integral is convergent, and the series is divergent if and only if the integral is divergent. So that's pretty nice because we know how to calculate these with, well, stuff we've already done, right? So now we can prove that that harmonic series was in fact divergent. Let's see why. So f of x equals 1 over x, it's positive. You calculate its derivative, it's negative, so it's decreasing, right? Thus study the integral from 1 to infinity of dx over x, which we know how to do that. We get the natural log of b minus the natural log of 1, which is infinity, so this integral blows up. Therefore, by integral test, the sum n equals 1 to infinity, 1 over n diverges by the integral test. Woo-hoo. This is, by the way, the p equals 1 series. And so, by the way, I should mention, before I forget, what's the answer here? the answer in 1, it's not the boxed answer, it's not what's boxed, it's not any particular thing here, it's the entire collection of thoughts, all right, with proper sentence structure and connectives, all right? So I know that's kind of shocking, perhaps, but in this part of mathematics, we actually expect you to write complete sentences and to explain yourself, all right? So, you know, try to start getting in that habit as you work on this. In fact, if you don't support your hypothesis for the test that you use, and you don't use sentences, and you just put equations down without words, I almost certainly am obligated to take off points. And to not take off points would be negligence on my part. All right, moving on here. The p-series result is the following. The sum n equals 1 to infinity of 1 over n to the p, it's convergent for p larger than 1, and it's divergent for p less than or equal to 1. So, to prove that, we use the nth term test for p less than or equal to 0. P less than or equal to 0, then by simple logic, 1 over n to the p is like n to a positive power, essentially, and that's going to go to either 1 or infinity as n goes to infinity. 1 if p equals 0. On the other hand, if p is greater than 0, we can calculate 1 over n to the p equals to 1 over n to the p is f of n, provided that we make f of x equal 1 over x to the p. But then, it's easy to see that that's continuous and positive on 1 to infinity. We also need to show it's decreasing, right? In order to use the integral test, we need to show it's decreasing. Calculus gives us an easy proof of that, because if we differentiate this, we get minus p over x to the p plus 1, which is clearly less than 0 for x in here, and therefore f is decreasing on 1 to infinity. So, we have already proved that p equals 1 is a divergent case. That's the harmonic series. So let's assume that p is greater than 0 and p is not equal to 1, and calculate. The integral of dx over x to the p, limit as b goes to infinity, of integral from 1 to b of x to the minus p dx is given as follows. So this is just the usual power rule for integration, and then we evaluate at b and at 1. Now, as b goes to infinity, this piece dies, and we're just left with 1 over p minus 1. On the other hand, if 1 minus p is, this is assuming that 1 minus p is less than 0. If 1 minus p is greater than 0, then this piece blows up, and we get divergence, right? So in summary, the integral of 1 to infinity of dx over x to the p converges for p greater than 1, and it diverges for 0 less than p less than 1. And so in total, we have the p-series result, which I wrote at the start, which is that the sum n equals 1 to infinity of 1 over n to the p is convergent for p larger than 1, and it's divergent for p less than or equal to 1. And that's the p-series result. By the way, something kind of neat to notice is that the integral of dx over x squared is actually equal to 1. But by more advanced methods, you can show that the p equals 2 series actually works out to pi squared over 6, which is, of course, not equal to 1. So it's important to realize that the integral test speaks to the convergence and divergence, but not to the precise value of the series. We do know this, that the integral from n plus 1 of f of x dx is less than or equal to s minus sn, less than or equal to the integral from n to infinity of f of x dx. So the remainder is bounded by these improper integrals, not starting at 1, but starting at n plus 1 and n. And this would be motivated by pictures very similar to those I already drew. But so let's use that estimate to try to truncate the p error in p equals 2 series after 3 terms. All right, so if I look at the series 1 plus 1 fourth plus 1 ninth plus 1 16th, in other words, the p equals 2 series, and if I just keep the first 3 terms, right, what's the error in just using the third partial sum? What's the difference between the actual sum and S3? So now I should into some terminology that's important. We already talked about the nth partial sum. This, whatever's left, is often called the remainder, or better yet, we could call this the tail of the series. And so the series minus the nth partial sum is equal to the remainder term, or the tail. And by pictures, again, similar to those I already drew, we have this estimate for the remainder. But we can calculate those directly for the p equals 2 series. All right, and so doing that, p equals 2, again we have this, which as b goes to infinity that drops out, and we just have 1 over n plus 1, and likewise if we integrate from n to infinity we get 1 over n, so that gives us the following estimates. 1 over n plus 1 is less than or equal to Rn is less than or equal to 1 over n. Now for n equals to 3, that means 1/4 is less than the remainder is less than 1/3, which means that the error in using the third partial sum for approximating the p equals 2 series is at most 1/3. And in this case I can check because I happen to know the actual value for the series by methods outside the course, okay? So if we add 1 plus 1/4 plus 1/9, we get about 1.36. This actually works out to pi squared over 6, which is about 1.649, and the actual remainder here is 0.2838, which is indeed between 1/4 and 1/3 as expected. And again, you don't actually need to know this to do what we did, right? The point is, even if I didn't know the actual value for the series, I would know for certain that it's between, you know, it can't be more than 1/3 away from this value. So I would have certainty that the value of the p equals 2 series was between about 1.03 and 1.69 with the work I've done here. All right? Okay, so that's kind of neat. Here's another example. Does the sum n equals 1 to infinity of n squared e to the minus n cubed converge or diverge? When I see something like this, it yells integral test at me because I know how to integrate the corresponding function of x. It's a u substitution, right? So we let f of x equal x squared e to the minus x cubed. We notice that f is positive, continuous. Differentiating f, we get this. And if you look at it, we've got a positive thing times this, which is clearly negative on 1 to infinity. So that shows you that since the derivative is less than 0, f is decreasing. Here's the sign chart, by the way. It flips from increasing to decreasing at the cube root of 2/3. Anyway, so f is, you know, continuous, positive, decreasing, and so we can apply the integral test. Let's do that. The integral of this is equal to that by u equals minus x cubed substitution. So this improper integral works out to 1 over 3e. Therefore, the sum n equals 1 to infinity of n squared e to the minus n cubed converges by the integral test. Very good. Moving along here, example 5, we're supposed to find the sum of n e to the minus 2n correct to 4 decimal places. So in other words, I want to know this, 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 and this, and I want these to be sure. So whatever uncertainty, it better be over here. So if I look at if I have an error of about 10 to the minus 5th, that'll suffice. Certainly suffice. That's probably actually a little bit greedy. Probably could do like 4 times this and still be safe. But anyway, I like to be you know, a little bit cautious, so I'll do 10 to the minus 5. Anyway, so integral. Now I'm going to think about integral test with f of x equals x e to the minus 2x. You can integrate by parts to do that integral. You can also check, and so at a minimum when you're doing this kind of problem, even if you don't check the conditions, you should at least claim they're true to convince me you're thinking about it. You know, sometimes I actually need to see details. It kind of depends on the bigger problem, or how obvious it is, or not obvious that these things actually are positive, continuous, and decreasing. But this is in fact positive, continuous, and decreasing. All right. Oh, by the way, I should mention, it actually suffices. You could replace 1 with m, and the same kind of test is true. We just start at 1 for convenience. If you could find a function which was continuous, positive, and decreasing past like 20, you'd still be able to say something about the series. What happens in the first few values doesn't really affect divergence or convergence, unless it's, you know, divergent at a specific value. But that setting that silly case aside. All right. Anyway, moving on. So the integral from n to infinity of x e to the minus 2x by the antiderivative that I just had a little bit up on this page is this, using FTC2 and the definition of improper integral. We apply L'Hopital's rule to make this go to 0. That's just obviously 0, and this works out to 1/4 2n plus 1 times e to the minus 2n. So we find the following estimate. This is less than the remainder is less than that, because that's the integral from n plus 1, the integral from n to infinity of our f. And then you just got to do some calculator work. So I call this thing Pac-Man, and because I think that's the larger one of these two. So I need this to be less than 10 to the minus 5. So I plugged in some calculator, plugged in some values, and I found that n equals 6 gave me this term of about 1.99 times 10 to the minus 5th, which is good enough. So that means we can use S5 for the desired accuracy. I think I have the rest of the calculation on the next page. So I've already showed that the fifth partial sum has an error in estimating the series of at most 2 times 10 to the minus 5. So calculate the fifth partial sum is this, which is equal to that, 0.180972. Oops, I forgot to round, 0.1810. By the way, you can check with Wolfram Alpha, and for example, it's not hard to use Wolfram Alpha to calculate the 10th partial sum, and if you do that, you get 0.1810154, which is very encouraging to me because it shows that if you took a bunch more terms, you'd still haven't changed these terms yet. In fact, Wolfram Alpha claims that the totality of the series works out to e squared over e squared minus 1 squared, but that probably means complex analysis, also known as Math 331 at Liberty. Allows direct calculation. Anyway, here are the tools we can use to estimate series to a desired accuracy. If we can do the integral, we can set up this, we can set up this bound between the n plus 1th integral from n plus 1 to infinity and integral from n to infinity of f of x dx. And so in so doing, we can squeeze the remainder, which is essentially the error, down between these two things. And so that gives us a way of estimating a series, possibly, to a desired accuracy. A little bit later, we're going to find an even better error estimation test for something called alternating series, which is even simpler and requires less calculation, but not always possible. Alternating series are special, particular cases. This integral test estimation theorem that I'm looking at here is good for, well, for any positive series at least. So, all right, well, that's it for this video, and the next one, of course, is just on p-series. Thanks, guys.